Welcome to this lecture for the course on thermal building physics, where we summarize the transmission processes for, in this case, heat transmission by convection. This is one of 3 topics for radiation, conduction, and as this lecture is about, it's for convection. And we'll summarize some of the ways to calculate heat transmission by convection by different formulas, as you will see as we come through the lecture here. First of all, heat transmission by convection, we can find the heat flow or we can find the heat flux, whether it's per area or not. And for that, we should actually find the convective heat transfer coefficient. But that is a way to calculate this that we will demonstrate by other means because it can be a little bit complicated, as we will demonstrate as we go through the subject. But with the heat transmission coefficient together with the temperature difference, then we can calculate the heat flow or the heat fluxes, and that's what we're really up to after having completed this lecture here. So for heat transmission by convection, we can also use the heat transmission coefficient, or 1 over that, which is the surface heat transfer resistance also in the same place. So at a surface, we have the transmission that takes place there. What would be much simpler, because this is for a fluid, which could be air, it could also be a liquid, but either if it's air or a liquid, well, it would be much simpler if we could regard those as being still standing, as if they were materials. But that is not the case, because these fluids are never still standing, but we can use it as kind of a reference if we thought we could compare to the situation with heat conduction in a still standing material, such as one of those 2 fluids. But that is not the case. The fluids are not still, but we'll use it as a reference, as we'll explain later on. So, but convection, then, that is the transfer of heat as it takes place between solid bodies and gases or fluids that circumfere the solid. So the heat transport will be dominated by one of 2 ways of causes for the things to happen. And that could be because of temperature differences that make a difference in density of the fluid that cause the motion in the fluid. That could be one cause. The other cause could be if we have an exterior force that forces the fluid to be in motion, and thereby also carrying with it some heat. So it can be rather complicated to calculate these convection processes. So indeed, it would be very difficult to do. But then, fortunately, many people have investigated that. So by experiments they've done, we have a lot of empirical knowledge that is put in literature. And such results from those investigations we should find. Our job, or your job, would be to identify which cases have been found in literature or where we have information and formulas. And then we can calculate or derive some relevant model numbers that characterize the phenomenon. So our job, your job, is to sort out what kind of case you are dealing with. And that could be for the flows that are either exterior to an object or to a surface, or they're interior within an object or a room or cavity or something. So that depends on the geometry that you must identify. Also, the types of convection can either be natural, that were the temperature-driven ones I just talked about, or they could be forced, where it was exterior forces that caused the motion in the fluid. And then the types of flow that you can have, they can be calm, and we call them laminar, or they can be more vigorous, and they would be turbulent. So we should also consider that, and there's even a transition regime, which is somewhere in between, if we should be very accurate. So for a flow over a certain surface, now looking to this type of flows here, well, then we could have a flow over such a surface here, as we see here, and that would be, in this case, nicely flowing here, but it could also be flowing around tubes or ducts as such. So that could also be outside an exterior convection that we have in such 2 example cases that you might be able to identify. And then you could also have flow within your object, as I've indicated already, in a confined or an enclosed geometry. So that could be within a tube, a duct, or something like that, a channel in a way. But it could also be that you have something in a cavity where the air circulates or the fluid circulates up and down within the boundaries of that cavity. So here is a slide that explains that you can have these internal flows, a little bit like was illustrated just on the slide before, or external flows on the slide before again. And then we could have the forces to be naturally driven by the temperature differences. Warm air rises, falls down on the cold side, and such things. But it could also be by the forced flow, where it could be in principle a fan that pushes the fluid, but it could also be the wind and such things. So when you have the flow, you should also characterize its nature. And if it's very calm, slow flow, it will be characterized by molecular layers that are flowing parallel to one another over each other. Then we have a velocity down at the surface over which we have the floor, where the velocity is 0, and then the velocity increases with the distance away from that surface. So it's a nonlinear increase of the velocity, so you have to know where you are in relationship to the surface. If you have the other type of flow, the more vigorous, the turbulent flow, well then again at the surface we have a velocity of 0, but very rapidly, much more rapidly than before for the laminar, then we have an increase in the velocity. And also the flow is not nicely, smoothly with layers over each other, but really a vigorous thing where things are also flopping up and down, if you will. Only in the very near to the surface layer, then we have actually also laminar flow. So what you could talk about a laminar sub-layer in that position. And I think that covered most of the things I said here, except one thing that is important to us, because we do all this because we want to calculate heat transfer. And then the heat transfer is much more intense when we have turbulent flow compared to if we have laminar flow, when you talk about heat transfer away from the surface that we're talking about. We're going to use for some of the calculations, if we calculate flows for instance, for water, which is a common fluid or liquid, of course, then we are going to use some material properties for water, density, thermal conductivity, and we have the dynamic viscosity and kinematic viscosity. And finally, we're also going to introduce the so-called Prandtl number here. So those are numbers that characterize the fluid, and they're somewhat temperature dependent, as this table illustrates. Likewise, also another common gas that we'll be interested in would be air, and then you can see the properties for air in a similar table like that. So those are numbers that you're probably going to use later on for calculations. Now we're going to introduce a certain number of model numbers, and the first one, the most important perhaps you could say, the central one, it's the Nusselt number. So it's a dimensionless form of expressing the heat transfer coefficient, which normally was hk as we introduced before, but now in a more general way, so it's dimensioned as. But it's characterizing the convection. As I said before, if we have air or liquid that were still standing, then we could just calculate the heat flow through those materials as if it were heat conduction. But because of the flow, we have normally a higher heat transmission than if it were still standing liquid or air. So therefore, the Nusselt number really indicates by a factor by how much more heat flow we have than if it were a still standing fluid. So if we can somehow get hold of the Nusselt number, that factor how much more it is, well then we can also calculate the heat transfer coefficient, as we will illustrate. So that's what we're all up to. That is really to find hk, but we do it via finding the Nusselt number. And here is the formula that tells about the relationship between the heat transfer coefficient and the Nusselt number. We should multiply the heat transfer coefficient with characteristic length and divide by the thermal conductivity of our fluid. Then we can find the Nusselt number. Or if we have the Nusselt number, we could of course isolate the heat transfer coefficient, as is very often the case, what you will do. So to calculate the flow, we also are interested in the flow velocity, and there we also you can use the velocity in meters per second, but as is characteristic here, because we want to generalize things as much as possible, then we characterize the velocity with a dimensionless number, which is the Reynolds number. So again, it's the velocity, but we multiply with a characteristic length, and we divide by the kinematic viscosity of our fluid, and thereby, with the units, if you check those, then the Reynolds number becomes dimensionless. There's no unit to it. So it can be kind of, you could say, general for us here. So we need a characteristic length. And what would that be? Well, it depends on the geometry. You have to take it out of the geometry. So if you have a flow over a plate, a surface, a flat surface, well, then it would be the length of the plate in the flow direction. So then the velocity could be taken directly when you need that in our formulas. You should take it as the velocity far away from the surface in the free flow field. Then, when you have calculated Reynolds number, then later on, as we've indicated, we need to sort out whether we have laminar or turbulent flow. And that's also a point where the Reynolds number is very important, because there are limits to the magnitude of the Reynolds number. If we're lower than 300,000, well, then we have laminar flow. And if we're above 500,000, then it's turbulent. And then we have, of course, what's called a transition regime in between there. So we need the distance from the front of the plate to a point where the flow is fully developed. That is called the critical length, and that is because the flow, as it passes over a surface, it starts in a laminar form, and then it makes later on a transition to becoming turbulent, and that happens then at this distance or length into the plate, which is the critical length. So we need a characteristic length. There can be different geometries, but here just shown some. As I said before, if you have flow along a plate, well, then the characteristic length would be the length of the plate or the point at which you are. It could also be along the exterior surface of a cylinder, as you see here. But if you have flow perpendicular to the cylinder, well, then the characteristic length would be the diameter of the cylinder as such. So there can be different values for the characteristic length, and what you should normally do is that you should check the author who has made the empirical investigations. How did the authors understand or define the characteristic length? But what I just showed on the previous slide was the normal settings for some geometries at least. Yet another model number. We need the Prandtl number. But as we said before, it was the last column in our table of material properties for our fluid, either the liquid, the water, or for the gas, the air, as we had in that table, or whatever other fluid that you are dealing with. So for water, the Prandtl number is rather temperature dependent, so that we must consider. Opposite it is for many gases, actually for air, but also for most other gases. The Prandtl number is a number which is very close to 0.7 and almost not temperature dependent. So it's a little bit varying if it's something that you should consider or not, that the Prandtl number varies with temperature. Yet another model number we need. That is a number we use to calculate if we have natural convection. It's the Grashof number. So the Grashof number is defined here in a little bit evolving formula here. The acceleration of gravity, the thermal expansion coefficient, so how much the gas, if it's a gas, expands with the temperature. Then the temperature difference that we are observing, a characteristic length raised to the power 3, and then we should divide by the square of the kinematic viscosity of our fluid. So that material property of the fluid that we should look up in the table. When we have the Grashof number, yet another model number that we very often see in the formulas that we're going to use later, it is the Rayleigh number. So again, it's a number that characterizes natural convection phenomena. Rayleigh number is the Grashof number multiplied with that Prandtl number we have for our fluid. So yes, it was for natural convection, but then we see very often, and now it comes to what we're really aiming for, formulas that tells us what would be the Nusselt number. And they could have, for instance, a shape like this. The Nusselt number is equal to this Rayleigh number, or this product here, multiplied with a coefficient c, and this Rayleigh number is raised to a power, to an exponent here, which is c1. So we need to find those coefficients, but that is what authors in literature have found in many, many cases that we can use for us. But they have found it in some characteristic cases, and then we can use their formulas for similar cases, even if our scale is different, because everything is worked out in dimensionless numbers. So it's important to note that we have all these empirical investigations, so we can find the numbers, but where is it really then that we find it? If it's, for instance, for a flow over such a surface as I've now indicated a number of times, are we finding it in a certain spot along the surface, or is it on the average for the whole length of the surface? So if it's a local value, we call it the Nusselt number at location x, Nusselt x. Or if it's the average number, then we can characterize it by the total length of the plate, or we also just put a line over the Nusselt number to indicate that it is an average value for the Nusselt number. Also, in order to have these properties of our fluid, I should say, we need, if they are temperature dependent, which temperature should we use, the one of the surface or the one of the fluid in the free flow field? Well, if you don't have any other information to go for, then you should take the average value of the temperatures when you decide what are the material properties as such. Now, for the rest of this lecture, I have just an arbitrary or some set of examples of places that you might be able to find in literature where people have found the Nusselt number depending on some situations here. And I think it's 6 examples with me. The first one is for a plane surface, a flat surface, where we have forced laminar, so slow, flow. And in that case, it means that the Reynolds number is less than 300,000. Then we can find the local Nusselt number in a certain position x according to this formula here. So that's kind of easy. All numbers are given here. Only we need to find the velocity by calculating the Reynolds number. That was the dimensionless velocity. We should find that Prandtl number for our fluid. That was for the local one, but also if we want to find the average over the whole surface, well then the Nusselt number becomes another formula, as you can see here, which happens in this case to be more or less the same formula, only with a factor of 2 for the coefficient in this case here. Example 2, that would also again be for a plane surface, but now we have forced turbulent flow. So that means our Reynolds number is big, more than 500,000. And then that's another formula that people in literature have found and given to us for the local Nusselt number at location x, according to this one here. There are certain conditions for which Prandtl numbers and Reynolds numbers where this formula is true. So that's something that one would typically find in literature if the conditions are okay for our case that we are dealing with. And again, you can also find the average Nusselt number according to, yes, just another formula. So identify the formula and use it again by calculating for your case the relevant dimensionless number, here the velocity Reynolds number, the Prandtl number for the fluid. And yeah, we need to find also the Prandtl number in the last term of this formula here. Yet another case here is again a plane surface. Here we have natural convection under isothermal conditions. And in such a case, people have found a formula a little bit like we saw from before. Nusselt number is equal to a constant and then the Rayleigh number raised to power C1. But in such a case, it depends, since it's natural convection, if we have a vertical surface or horizontal surface, and if the surface is horizontal, is the heat flow up or down is something that we should consider. Because then there are different values for these coefficients as people have found them in literature. So again, identify which case you are dealing with, find your spot in this table, and then read those numbers that you have. Here's a range of validity for the Rayleigh number that that can be used, but very often covers the cases that we are interested in. Yet another case, that's flow between two parallel surfaces now. So in this case, rather special perhaps, but we have one surface which is well insulated. We call it that it's adiabatic, so there's no heat transmission through that surface. But there is to the other surface which has a certain constant temperature. So in this perhaps special case, I don't know, but you have to identify it and see if it compares to your situation. Well then, authors have found this formula here for the Nusselt number, and again you have to identify the characteristic parameters that you can put into the formula to calculate the relevant dimensionless numbers. Yet another case again. It has 3 variations, and this is variation A of a case with flow between two parallel surfaces. But those surfaces can be either vertical, sloping, or becoming more and more horizontal. And that's what we have the 3 different cases about here. So first of all, if it's a vertical cavity we have, well, then the Nusselt number for this case, 90 degrees slope, you could say, is a formula that you must calculate. There are 3 values to calculate, and then you should take the maximum of that. Well, that's what people in that literature here have found. So that's something you can, again, insert the relevant numbers, but here you have to calculate the Rayleigh number by, as you've seen previously, as a product of the Grashof number and the Prandtl number. And that's a certain notion of validity for this formula. But that's something that you can calculate. And that's, again, just to identify the case you have and then just make the calculation. So we can turn the cavity a little bit, so now it has a slope. Now if the slope is 60 degrees, well, then we have another look of the formula here, and you have to calculate, in this case, what it is then. If you don't have a completely vertical or completely 60 degrees value for the slope, then you can interpolate between what you find from this slide and from the previous slide. Finally, if we have the cavity to become still more flat or more horizontal, well, then with the slope theta here, you can insert in the formulas now also, and then you can find yet another average value for the Nusselt number that expresses the heat transfer between the fluid that flows between the surfaces, in this case here, in our case. Example number 6. Now we're looking to flows around something, and that would be around a tube or around a duct, where we have forced convection, just the case I've taken with me here today here. So again, we have a formula looking a little bit similar to some extent to formulas we've seen before, with the Reynolds number and the Prandtl number raised to some powers and a coefficient. And there are some ranges of validity for some of those values and geometry that we should look to and check if it corresponds to it. Now, what we need to do now is to have values for those coefficients and exponents, and that comes then typically perhaps in a table, like here on the next slide here. Depending on the geometry, whether it's a circular or a rectangular shape, and you can read the geometry inputs here. Well, it tells you how you should calculate the Reynolds number. So the D, the diameter here, would be the length that you insert for the characteristic length when you calculate the Reynolds number. And then you see where you end up, and you can then find values for the coefficient and the exponent that you're gonna use. So that was example number 6, and that more or less completes it. It's not completed entirely because it's really endless what you can find in literature, almost. But these are some very typical characteristic cases that we can also find use of in many engineering and building related applications. So with this, you got some introduction to how to calculate in practice with the convection, which should indeed be very complicated, but when we boil it down to this sorting of values and identifying formulas, then it's actually possible to make it yourself. And now you can go home and make some exercises and try it out for yourself. So thank you for listening into this. I hope you enjoyed it.